Hello everybody and welcome to my fifth video. This is on ternary circuits. I'll be using the B.I.T.L.O.N technique, which is a binary implemented ternary logic output network. Basically what that means is you convert a ternary signal into binary, process it in binary and then convert it to ternary. So here we have a few maximum and minimum of transistor circuits. This is used because it's easy to realise this in circuitry, the maximum and minimum functions. But there are certain disadvantages. One is there's no way, noise is transferred to the output from the input, and there's no way to determine the logic state for a given voltage. So the requirements for our logic circuits are we need voltage comparison circuitry to detect the logic state on the inputs, and the voltage must remain constant for a given logic state on the output of the circuit. So here we're going to split the ternary signal here into two binary signals. Two binary operators, A1 and A2. Now this is like voltage comparison. So anything between 0 volts and 0.8 volts is a logic 0 for A1. And anything between 2 volts and 5 volts is a logic 1 for A1. And anything between 2 volts and 0.8 volts is undefined. For A2, anything between 0 volts and 3.8 volts is a logic 0. Anything between 4 volts and 5 volts is a logic 1. And anything between 4 volts and 3.8 volts is undefined. So we split these two codings, A1 and A2, at different voltage levels with different logic 1s and 0s. And we combine the two to get the ternary voltage range here. So logic 2 is between 5 and 4 volts. Logic 1 is between 3.8 volts and 2 volts, and logic 0 is between 0.8 volts and 0 volts. And then 2 volts, 0.8 volts is undefined, and 3.8 volts to 4 volts is undefined. I'm using Schmitt triggers for these circuits A1 and A2, and for A2 I've used a level shifter to get the level of the undefined region shifted up 2 volts. So it should be from 2 volts to 4 volts. This is the circuit diagram for A1 and A2. I'm using a 74ACT14 hex Schmitt trigger. Now here it's completely connected to the input A. And A1 is just goes through two inverters to get the output. Output is binary, the input is ternary. From A2, this is the level shift of 2 volts from base to emitter resistor. So there's a 2 volt voltage drop from there, 0.8 volts from the base emitter junction, and 0.6 volts from the two diodes. Or each, 0.6 volts each from the two diodes. That makes approximately 2 volts. So this is the A2 output, and that's also binary. So using two 74ACT14 Schmitt triggers. So the coding for A1 and A2, if A is the ternary input, 0, 1, 2. If A is a 0, A2 equals 0 and A1 equals 0. If A is 1, A2 is 0 and A1 is 1. If A is 2, A2 is 1 and A1 is 1. So in general, AN equals 1 if and only if A is greater or equal to N and 0 otherwise. So this is the part where we convert the binary into ternary. This is the output diode resistor network encoding. Now there are three types of output resistor diode network I've used. Circuit A is here, and that gives a 0 when F2 equals, well, F is ternary here, which is the output. F1 and F2 are the binary inputs to the resistors. Well, a 0 on F1 and F2 would be 0 volts, and a 1 on F1 or F2 would be plus 5 volts. So for circuit A, to get a ternary logic 0, F1 and F2 have to be 0. To get ternary logic 1, F2 is 0, F1 is 1. The ternary logic 2, F2 and F1 are 1s. For circuit B, well, I've used a Schottky diode here. I've used a Schottky diode because it's only got port 0.3 volts voltage drop, as opposed to a silicon diode which is about 0.6. So it's just less upset to the network biasing. So that diode there means I can introduce a don't care state here, because when F2 is a 1, F1 can either be 0 or 1. Because if F0 is a 0, this diode's reverse bias, so no current flows through that resistor. So F1 can be a 0 or 1. For circuit B, if F is a ternary 0, F2 is 0 and F1 is 0. If F is a 1, F2 is 0 and F1 is 1. If F is a ternary logic 2, F2 is 1 and F1 is a don't care state. Circuit C, I've introduced a Schottky diode into F2, and that means that F2 can be a don't care state at F equals 0. Reason for that, if F1 is 0, it doesn't matter whether, if F2 was a plus 5 volts, this diode would be reverse biased. So it doesn't matter whether F2 is a 0 or a 1. So for F, if F is a ternary logic 0, F2 can be a don't care state and F1 is 0. If F is a ternary logic 1, F2 is 0 and F1 is 1. And for a ternary logic 2, F2 is 1 and F1 is 1. Right, if you're going to build some circuits, you're going to need a signal generator and a clock to test your circuits. Now this is such a circuit. Here we have a 5 MHz TTL oscillator generating a clock signal, and this stage generates the ternary signal. This is the least significant trit standing for ternary digit, TRIT, and this, you can daisy chain this circuit up. This is the clock for the next circuit, which would be your input to the next circuit here. Basically, it's a 2-bit synchronous counter generating the signal 012, 012, 012 repeated, and as I say, you can daisy chain as many of these as you want. You don't have to use this TTL oscillator. You could quite easily use a 555 timer to generate a clock signal. It's entirely up to you. But these, if you do use this, these flip-flops have to be 7/4 ACT 7/4s, because the clock has to be TTL compatible. Here we have the successor function. This is from, these are the functions for, well, the unary operators for the post algebra I did a video on, so if you want to check that out, that'd be great. The successor function just adds 1 to the input A modulo 3. So a 2, 1 to a 2 is 3, so modulo 3, that's 0. Here we have A1 and A2 in response to A, and A plus 2 and A plus 1, which is the function. So what I'm doing is I'm taking this value and looking up the value there and placing it there. So A plus is a 1, A plus 2 is a 0, and A plus 1 is a 1, which is there. A plus is a 2, both A plus 2 and A plus 1 are 1s, that's there. And A plus is a 0, so A plus 2 is a don't care state, and A plus 1 is a 0, that's there. So if I didn't have that don't care state, I'd have to use an AND function, because this would be a 0. So that would have to be A1 and not A2. But because I've got a don't care state there, I can just reduce it to A1. And similarly, A plus 1 is not A2. So A plus 2 is A1, and A plus 1 is not A2. This is the circuit diagram. This is the whole B.I.T.L.O.N example of the whole B.I.T.L.O.N technique. You take the ternary circuit, ternary voltage level A, you convert it to binary here, you process it in binary, and you convert it into ternary here. So this is a circuit, this is A1, and this is not A2, and I've used circuit C with a Schottky diode there to convert it back into ternary. You can use any Schottky diode, small current diode. I've used a B.I.T.L.O.N, and for the silicon diodes I use 1N4148. There's a 390 ohm resistor there, and I've used a BF11199 there. One thing I should mention, which I forgot to mention, going back to the output resistor networks, if you're using 7.4 AC or ACT logic, the resistor is 240 ohms. If you're using 7.4 HCT or HCT logic, the resistor is 1.3 kilo ohms. This is just so if you short F to earth, you don't exceed the maximum load of the output capability, the output current capability of the gate. For ACT and AC, the maximum output is you can sink and source 24 milliamps. For HC and HET, the maximum is plus or minus 4 milliamps. So the only thing that needs to be HCT or ACT is the input comparator circuits. So they're the 7.4 ACT14 or 7.4 HCT14. Right. Here you have the predecessor function. This takes 1 away from A, modulo 3, so 0 minus 1 is 2, 1 minus 1 is 0, 2 minus 2 is 1. Here we have again the inputs for A and B, the binary coding for A. Here we have the coding for not A minus, or A minus, should I say. Here we have a 2 here, which is a 1 and an X in the don't care state for A minus 1, and a 1 for A minus 2, which is here. Using network output resistor network B. A minus is a 0, A minus 2 is a 0, A minus 1 is a 0, there, and A minus is a 1, A minus 2 is a 0, and A minus 1 is a 1, which is here. So, because I'm using a don't care state, I can reduce A1 to A2, A minus 1 to A2, sorry. If I didn't have that don't care state there, A minus 1 would have to be not A1 or A2. But since I've put that in, I can reduce it to not A2. And A minus 2 is not A1. So A minus 2 is not A1 and A minus 1 is A2. This is the circuit diagram, similar to the successor function. We have not A1 here, A2 here, and using circuit B with the Schottky diode, you get the A minus, ternary A minus. We have the diametrical inverter function. Technically you don't need this, but I've just put it in to show what the binary processing is. Use circuit, I'll put circuit A for this. Basically, 2, you have the input 0, 1, 2 and your codings A1 and A2. So A bar, the diametrical inverter function, just reverses the order of the truth table. So 2, 1, 0 in response to 0, 1, 2. So 2 is a 1, 1 there, a 1 is a 0, 1 there, and a 0 is a 0, 0 there. So A bar 2 is not A1, and A bar 1 is not A2. So we have the function. So this is not A1 and not A2. Just combine them to get A bar. Here we have the two-valued union operators. These are the union operators for the post-algebra I published a video about. So basically A1 gives a 1 when A is a 0 and a 0 everywhere else. A2 gives it a 2 when A is a 0 and a 0 everywhere else. And this is how you implement them circuit-wise. Basically you just have a Schmidt trigger, 74SH14 or HC14, and you divide the voltage to half. So when this is a 1, this is a logic 2, this is a logic 1. And for A2, it's just a straight Schmidt trigger to get this output. These are the two-valued union operators for the other algebra presented in the video. If you'd like to go watch it, please do. So for A00, 0, basically if A is between these two values, then it's a 2 and a 0 otherwise. So A00 when A is a 0 is a 2 and a 0 otherwise. A 1, 2 is when A is a 1 and a 2. A1, 2 is a 2 when A is a 1 or a 2 and a 0 there. A1, 1 is a 2 when A is a 1. A0, 1 is a 2 when A is 0 and 1 and 0 2. And A2, 2 is a 2 when A is a 2 and a 0 everywhere else. So this is circuit diagram A, similar to the one on the previous page. This is B, just the opposite of A. This is, to get the A1 you have to have an AND function and not A1, sorry, A1 and not A2, and AND them together to get A11. And lastly, the diagram D, A01, you have to use A2, and it's basically not A2. And for circuit E, it's A2 to get A2 too. Next we go on to the binary operators. This is the minimum of function. Takes a minimum of whatever it's on its inputs A and B. I've done one for two inputs A and B, but it can be for more. And basically, this is your coding for A, this is your coding for B, split into A1, A2 and B2 and B1. And I'll split the output also into two sets, A1 and A2. Sorry, A and B1 and A and B2. So if you do a Kerner map of this, it turns out that A and B2 equals A2 and B2. And A and B1 is A1 and B1. A1 and B1. Yeah. So if you do a Kerner map for this, just to test it on right, and be aware that A2 is a 1 and A1 is a 0 is a don't care state, and so is B2 is a 1 and B1 is a 0 is a don't care state. Or rather a can't happen state. So this is a circuit diagram for the minimum of function. Basically I've used De Morgan's theorem here and changed the AND to a NOR and inverted all the inputs. This, if I used an AND, I would have to use 2 Schmitt triggers per input, which means I'd use 8. So I only use 4 and save some gates, because that means you only get 6 hex Schmitt triggers in a gate. So I'd have to use 2 chips. So this way I can get away with using 1 chip, using De Morgan's theorem and using the NOR circuit. So resistor output A, output network A, just 2 resistors. Well, if you were using HC or HCT, these resistors will be 1.3 kiloohms instead of 240 ohms. I think I mentioned that before. Here we have the maximum function, and again it's a binary operator. It requires at least 2 inputs. Well, this is input A and B, and it takes a maximum of whatever is on its inputs A and B. So this is the output A and B, A max B. And again, I've coded the inputs A and B into A1, A2, B1, B2. And if you do a Kerner map of this, I've split the output A max B into A max B2 and A max B1. Do a Kerner map of that, and A max B2 is A2 or B2, and A max B1 is A1 or B1. I've done a similar trick with the circuit diagram as I did with the previous circuit. I've used De Morgan's theorem and changed the OR into a NAND and inverted all the inputs. This, for the same reasons, it just means I can use 4 Schmitt triggers instead of 8, and similar type of output resistor network A. This is the difference of function. What I didn't specifically design this function. I just wondered what would happen if I use an exclusive OR function for both, because I've had an AND function for the minimum of function, an OR function for the maximum function. I just wondered what would happen if I use an exclusive OR function. So the difference of function is a 2-valued, only binary operator. It's only got 2 inputs, A and B, and A tilde B is the difference of whatever on its inputs A and B. So 0, 0 is a 0, 0, 1 is a 1, 0, 2 is a 2, 1, 0 is a 1, 1, 1 is a 0, 1, 2 is a 1, 2, 0 is a 2, 2, 1 is a 1, 2, 2 is a 0. This is handy because you can compare whether two inputs are equal or not, because the output will be 0. So anyway, I've coded the inputs A and B here, A2, A1, B2, B1. I've split this into two sets, A tilde B2 and A tilde B1, and basically a 1 can equal a 0, 1 or a 1, 0, and a 0 is a 0, 0 and a 2 is a 1, 1. So just by A tilde B2 is A2 exclusive of B2, A tilde B1 is A1 exclusive of B1. This is a difference of function circuit diagram. Basically, if you negate both the inputs to exclusive OR gate, it performs the same function. So instead of using 8 Smith triggers, I can get away with using 4. So these are negated inputs there and there. They perform the same function, so this is the circuit diagram. I'm using again resistor network A with no Schottky diode in there. And now we get onto the flip-flops. So I'm going to use two binary SR flip-flops and convert them and use them to form a ternary SR flip-flop. I'm going to use the NAND circuit. This is Q, S and R, Q, S and R and not Q here. This is Q2, not Q2, S2 and R1, and Q1, not Q1, S1 and R2. So S1 and S2 are the binary codings for S, and R1 and R2 are the binary codings for R. So if S2 and R1 is a 1, both 1s, it's Q. If R is a 0 and S is a 1, it's a 0, Q is a 0. If R is a 1 and S is a 0, Q is a 1, and a 0, 0 is prohibited. And the same for this circuit using S1 and R2. So this is the SR flip-flop. Basically Q2 is S2 and R1 and Q1 is S1 and R2. So Q2 holds S1, S2, not S2 is a 1 and not R1 is a 1. That's Q2. Not S2 is a 1, not R1 is 0. Is a 0. Same here. You've got a 1, 1 there, which is Q2. A 1, 0 there, which is 0. 1, 0 there, 0. S2 is 0 and R1 is a 1. And these are zeros which are prohibited. Same for Q1. You've got S1 is a 1 and R2 is a 1, so that's Q1. Same thing here. Not S1 is a 1, not R2 is a 0. Gives a 0. Not S1 is a 1 and not R2 is a 1. Gives a 1. Same here, same here, same here. Here 0, 0 is prohibited and there 0, 0 is prohibited. So we're left with a ternary function overall. So when S and R is a 0 you get Q, hold. When S is a 0 and R is a 1 you get either a 0 or 1, because that can be either a 0 or 1, but that has to be 0. So that's 0 or 1. When S is 0 and R is a 2, Q is a 0, 0, 0, reset. when S is a 1 and R is a 0, it's a 1 or a 2. Hold a 1 or a 2, that's because Q2 can equal 0 or 1. So that's either a 1 or a 0. Ternary 1 or 0. Sorry, a ternary 1 or a ternary logic 2. 1, 2. On S is a 1 and R is a 1, Q is a 1, 0, 1, set 1. Prohibited. When S is a 2 and R is a 0, Q1 and Q2 are 1, so that's a set 2 here. And you've got prohibited states there. So that's the function table for the SR flip-flop. This is the circuit diagram for the SR flip-flop. This is Q2 and Q1, not Q2, not Q1. Q2 uses S2 and R1, and Q1 uses S1 and R2, not S2 and R. Sorry, I'll start again. Q2 uses not S2 and not R1, and Q1 uses not S1 and not R2. Right. Basically, you use the two NAND circuits, connect the Q1s and Q2s via the resistor network A, and the not Q via resistor network A to give Q and Q bar. Q bar is a diametrical inverter I showed you in the previous circuits for union operators. So, one thing I will mention, which I don't think I've mentioned before, is if you use a BF199, you can use any radio frequency transistor. Don't use an audio frequency transistor for this, it won't work. You have to use a radio frequency transistor. Okay. Next we have the D flip-flop. Well, if there was ever a reason to use this system, this is it. Because basically, if you're going to design any logic circuit, you need flip-flops. There's no, most circuitry you do or use all design will involve flip-flops. So this is the easiest way to make a D flip-flop. Rather than using the SR method and using a master-slave flip-flop, using two Ternary SR flip-flops, you can do this just by using two binary D flip-flops. So what I've done, I've converted the inputs from ternary logic D input, converted it into binary A1 and A2, stored it using the flip-flops, provided a clock here, and connected the outputs Q1 and Q2 via diode resistor network A and not Q2 by diode resistor A to give ternary Q and ternary Q bar. Like I say, as with the SR flip-flop, Q bar is a diametrical inverter. So the clock these are positive edge triggered flip-flops. So the clock will trigger these flip-flops on a negative going edge from a ternary logic 1 to a ternary logic 0. And I've included set and reset inputs here. The not set, when not S is a 0, it sets Q to a 2. When not R is a 0, it takes Q to a 0, sets Q to a 0. I'm using 74AC-T14 here. Right, that's basically it. There's nothing to stop you from using more than one input here and having a clocked function for some reason. If you wish to do that, you could, instead of just using flip-flops as they are. Using the flip-flop as it is, you could clock any function. All you have to do is get F1 and F2 and clock it using these and apply a clock. I think that's basically it, really. You can use this in conjunction with other functions, unit operators, to build counters and stuff like that. I mean, if you connected the successor function, the input successor function from Q and the output to D, and applied a clock, this would cycle up 0, 1, 2, 0, 1, 2. So you can make a counter quite easily that way. I mean, there's loads of variations you can do, but I think that's basically it. So I'll leave it there. Well, I hope you've enjoyed it. That concludes the presentation. Thanks for watching. Bye.